Welcome to Learning to Engineer. So far, we've been discussing about op-amps in a great detail. We also saw the applications of op-amps. Op-amps have a collection of electronic devices inside it. They are used everywhere in computers, in calculators, sensor, measurement circuits, instrumentation circuits, in any amplification devices in everywhere. They have a collection of MOSFETs or JFETs or BJTs used in differential amplifier configuration. These BJTs are a primary amalgamation, I would say, or maybe a primary extension of diodes. These BJTs are made up of the P and N materials, which is primarily used in diodes. These diodes are the first devices which was formed using semiconductor materials. We are going to talk about the operation of diodes, how they are made, how they function, their characteristics, and all in this video. Let's get started. The semiconductor materials have a conductivity between the conductors and the insulators. The conductors have conductivity ranges which is very high, which is more than 10 power 2. These are typically the metals who have more free electrons in their valence shell. By application of a little amount of energy, these electrons can move from the valence band to the conduction band. The valence shell is the last shell of an element, and all these electrons are attracted to the nucleus by a magnetic pull. If you have more electrons in the outer shell, it will become difficult for us to etch each one of them out of a valence shell. Whereas in conductors like metals, say for example manganese, iron, silver, gold, copper, in all of these good conductors, we have very few electrons in the valence shell. By the application of little voltage, which we call as the energy, we can move them into the conduction band and they facilitate the conduction. What is conduction? Movement of electricity inside a material is conduction, right? When the electrons move in one direction, the direction of the conventional current is in the opposite direction, which we call as holes. Okay, when the electrons move from right to left, the current moves from left to right. That is what we say. We call this as the direction of conventional current. In metals, the electrons easily move from the valence band to the conduction band, so they act as good conductors of electricity. Whereas the insulators have more number of electrons in their outer shell, this makes them more stable. So we can really not pull them out of their valence energy level into the conduction level and make them conduct electricity. So these band of semiconductors fall between these two ranges. Okay, so for example, if we see the electronic structure of manganese and iron, we have only 2 electrons in the valence, whereas from the insulators, if we observe, they have more number of electrons. You can find them in the periodic table. They will be arranged here. Okay, if you consider semiconductors like silicon and germanium, gallium arsenide, they will have 4 electrons in the outermost shell. First of all, we'll understand about stable octect configuration. When an element is said to be stable, they will have 8 electrons in the outermost shell. When there are 8 electrons in the outermost shell, say for example, if iron has 8 electrons in its outermost shell, this iron will be very stable, and no matter how much energy you apply, they will not move out of its electronic configuration. That is called as stability. But they have only 2 electrons. So it's easier to make these 2 electrons move and hence conduct electricity. Whereas if you take the semiconductors like silicon and germanium, you have 1, 2, 3 and 4. Same is the case for germanium. You have 1, 2, 3 and 4. 4 electrons in the outermost shell, so which makes them non-conductors by nature. By making them react with some impurities, we can make them good conductors of electricity. Let's see that. Silicon is basically sand. Okay, so how can we make sand conduct electricity? We are going to see that. Pure silica is used as a substrate material. Silicon in its pure form is added to some pentavalent impurities like antimony, arsenic and phosphorus. Arsenic and phosphorus, all these three are pentavalent impurities. What is pentavalency? They have 5 electrons in its outermost shell. This silicon will have 4 electrons in its outermost shell, and these pentavalent impurities will have 5 electrons in its outermost shell. So as a result, they will have 9 electrons. So 8 electrons can be held in the 8 electrons can be held in the outermost shell, and 1 electron is called as the free electron, which is used for conduction. This electron is not attracted by the pull of the nucleus, hence it will be able to freely move around the electronic space. So this will be used for conducting current, and these materials are called as N-type materials. Why it is called N-type? Because electron which has negative charge is free to move around. This can also be done in another method. You can also have a pure silicon which has 4 electrons in its outermost shell react with trivalent impurities. What happens because of this? They have 4 electrons in its outermost shell, and when it reacts with elements which have 3 electrons in its outermost shell, so totally you will have select electrons with one space to hold an extra electron, and this space is called as a hole. So this is how we form p-type materials. Okay. In p-type materials you will have one hole, and in n-type materials you will have one free electron. So this free electron, when it comes in contact with this hole, this will occupy this position, and hence this will be a stable element. I'll ask you a question. If this is being made stable, then how can they conduct current? In diodes, you all know you have a p-type material. You have a bar of p-type material. P-type means silicon with trivalent impurities, which is attached to n-type material. This is silicon with pentavalent impurities, and this is silicon with trivalent impurities. Okay. So when both of them are brought close to each other, the excess electrons in the n-type material will combine with the excess holes in p-type material. These excess elements are called as majority carriers. In n-type materials, the majority carriers are electrons, and in p-type materials, the majority carriers are holes. Okay, so when they are brought close to each other, they become an insulator. What's the use of it? Because when you are passing current through a battery, you are just applying potential to it. So when you are connecting a battery to this material in this fashion, this is called as forward bias. I'll come to that later. Okay, so if you are connecting battery in this fashion, the electrons will flow into the negative terminal or the n-type terminal. Okay, the electrons will flow into the n-type material, and the direction of conventional current is from positive to negative. Okay, but the electrons flow from n-type to the p-type. So as you apply more and more potential to it, more amount of electrons will be crowding the n-type material. As a result, this depletion region, which is formed by the recombination of electrons and holes, they get broken. So as it crosses a particular threshold voltage, this depletion region, which is formed by hole electron recombination, gets broken, and a small channel is formed inside it. So through this, these electrons which is pumped will seep through the N-type material, it will move to the P-type material and it will reach the positive end of the battery. So this is how the electron travels in a PN junction when it is forward biased. What is forward biasing? When a positive terminal of the battery is connected to the P-type material, this is called as forward bias, and above a particular voltage amount the conduction happens, and this voltage is called as forward bias voltage. Say for example you are reversing the battery. So to this bar, this is P-type and this is N-type. Okay. So the electrons are pumped into the P-type materials. Okay. So P-type material means what? It will have excess holes. So all these electrons, it will be occupying the P-type materials holes and the depletion region will widen. There will already be a depletion region because of the hole electron recombination between the P and N elements. Now what happens? These electrons which is pumped by the battery, they crowd the P and N junction and the depletion region widens. The layer becomes thick and thick and thick, and beyond a certain voltage level called as the reverse breakdown voltage, there is conduction happening, but at this point there is no use. This diode would have worn off because of excess pressure. This is called as reverse bias. This is called as reverse bias. In reverse bias, we will be connecting the positive terminal to the N-type material and negative terminal of the battery to the P-type material, where we are forcing more and more electrons to the P-type material, and these electrons occupy the holes which is already present in the P-type material, and they will contribute to the widening of the depletion region. So in reverse bias, conduction doesn't happen, and in forward bias, conduction happens. For this reason, diodes are used as filters to remove the negative component of a signal. Say for example, you are passing AC signal. I'll draw the diagram. This is the symbol of a diode. This is the P junction and this is the N junction. Okay. Let's say for example, to this diode, I am applying a AC signal. You have a load and you are applying a AC voltage through it. Let this be of sinusoidal nature. Okay. When you are passing this through a diode, what happens? It will only pass the positive half cycle, because when you are supplying negative voltage to the diode, what is negative voltage? More and more electrons will be pumped into the P junction, and hence conduction doesn't happen during the negative part. So during this part, no conduction happens, and the diode conduction happens when you apply a positive voltage. So as a result, RL will receive only the positive half cycle and there won't be any conduction in the negative half cycle. This is how diodes are used in rectifiers. There are many kinds of rectifiers which you will be learning in power electronics. That's not the intention of this video. I just want you to introduce diodes to you. We saw how a diode is formed from silicon. We have a P-type material, we have an N-type material. By combining both of them, we create a depletion region on its own, and by applying a positive voltage, this depletion region breaks down and you will have a electron conduction happening from the P to N junction. Thereby the electron flows into the circuit and creates conduction, whereas in reverse bias, conduction doesn't happen. Okay, so how do we find the value of the current through the diode? This is governed by Schokleys equation. Some people call it a Schokley, some people call it a Schokley, however it is you can call. Okay, so the diode's current is equal to the reverse saturation current times e to the power Vd divided by Nvt minus 1. I'll explain you. Okay, this is reverse saturation current. At what current in the reverse bias the diode gets saturated? You can find that in the data sheets. Okay, Vd is the forward bias potential. What is Vt? Vt is K into the absolute temperature of that medium divided by the unit of charge. Q is 1.6 into 10 to the power minus 19 coulomb, which is the charge of a unit electron, and K is the Boltzmann constant, 1.38 into 10 to the power minus 23 joule per Kelvin, and temperature is measured in Kelvin. Okay, so Vt refers to this value, and N is the ideality factor. Considering that this is ideal, N is mostly 1 in usual cases. Wherever you are trying to find out this, ideality factor is mostly considered as 1. Okay, so by this we are getting the value of the diode current. There will be some simple problem asked based on this formula, and I hope you will be able to solve them on your own. Okay, in next class we will be seeing the application of diodes in clipper and clamper circuits and some problems based on them. Thanks for watching. Do subscribe to my channel and ring the notification bell to get a regular update on your mobile phone once I publish my next video. Thank you.